Good afternoon, folks. Let's just let everybody in and then we'll get started. Just give it another minute or two. All right, how's everybody doing today? Hanging in there, hanging in there. All good stuff, I hope. Just give me a moment, we'll get started. See, we got a couple of people coming in still. All right, let's get started. Okay, hold on, just setting up my two screens here. Always a fun time. So we are on lecture 8. I had opened it for everybody so long, so if it didn't go for you, then we'll figure that out. Stick around after class and I'll help you with that.
Okay, thank you.
You're welcome.
I emailed you, but you didn't.
I extended the due dates. I saw I had some emails, but I remembered I extended it, so I didn't think it was an issue. I'll check into it.
Okay, thank you. It didn't work for me.
Okay, not a problem. We'll work everything out. Okay, folks. So, welcome to lecture 8. Today, some of the topics we're going to talk about include the Jovian ring systems. Right, we're going to look at the rings of Saturn a little bit, and just get a sense of what's going on in some of those rings. We're going to look at the difference between meteoroids and asteroids and comets, and what do they look like and where do you find them. And then we'll talk about dwarf planets, specifically the hot topic amongst many millennials of Pluto and why Pluto is no longer considered a planet. And we will also explore a little bit about extrasolar planets. And we'll talk about what that word extrasolar means a little later on in the lesson. So we're going to start with Saturn's rings. In the image on the left, you can see what Saturn and its rings look like from Earth. Saturn is often considered the crown jewel of our solar system. Its rings make it the most, I think, well, this might be a little bit subjective, but one of the most interesting things to look at in our solar system. And its rings are very, very thin, very, very thin. But the rings are not solid, right? The rings are actually made of very small particles of ice. And so in the image on the right, this is another, both the image A and image B are real images. Image B is taken from the Cassini spacecraft. Again, we're going to be hearing about that a little later on when one of your classmates does their space mission assignment presentation. Cassini. And we can see here that within the rings, there are these, small little disks, regions where there are no, or there is very little matter. We can see regions where there's a lot of matter, right? But there are gaps between, within this larger ring-shaped thing around Saturn. And so the reality is that each one of these is a little ring, right? There are many, many rings with very narrow gaps that separate them. And each of the rings has a different name, so that, and usually that corresponds to a letter, so that we can address which ring we're talking about. This is an artist's rendition of what that ring system around Saturn looks like. And we believe that it looks like these very small, or well, I mean, I shouldn't say very small, because these are 10 to 20 meters across, but clumps of ice that have been brought together by gravity that orbit in a very, very narrow disk shape around Saturn, specifically in its equatorial plane. And so within the rings of Saturn, where those tiny little balls of ice orbit, there are also tiny little moons. We call them gap moons. And you could probably figure out that it's because they exist within the gap of the rings. Right, so you can see here in this top image, this is 13 times zoomed in from the bottom image. Right, we're looking at 100 kilometers across, which is plenty of, I mean, that's a pretty large distance. Central Park is what, like 5-6 kilometers along, from 59th Street up to 110th, something like that. So this is pretty large here, that what we're looking at. And what we notice is that the gap moon actually creates these little ripplings on the inner and outer gaps, where the gap moon's gravity is causing a speeding up of the, well, it's causing the particles that are on the inside of this gap to slow down a little bit as they're moving faster than the gap. Remember Kepler's law, the things that are moving, that are closer in, tend to orbit faster. So the gravity from this little gap moon is pulling back, and it's causing these periodic ripples. And we're getting something similar on the outside, where the gap moon is moving faster than the outer part of the ring. And so you're also getting a little bit of rippling. And you can see that there are multiple gap moons here. There's one where my mouse is. Here's another one in this zoomed in region, which we can see up here. And so we've got gap moons. We have shepherd moons, right? Moons that sort of orbit on the inside and outside of different parts of the rings. So like here's the F ring. This is the one of the outermost rings of Saturn. And what the perspective that we're looking at here is, like, imagine that you're holding a, gosh, if I said a CD, how many of you would know what that is? Imagine we're holding some kind of disc, and we're looking at it from the underside, right? Then the part of the disc that's on the top, that's closest to us, would be the top part of the ring, and the part that's farthest would be the bottom part. So that's what we're seeing here, is that this ring at the top, I'll highlight it for you. And this is the side that's closest to us. And the side that's not highlighted is the side that's farthest away from us. And you can see how, if I were to, well, I gotta get the eraser out here. You can see how Pandora, when it says it orbits outside the F ring, you can tell that the ring doesn't appear to cut in front of it. That's how we know from this perspective that Pandora is closer to us than the outside of the ring, than the ring itself. So it has to be on the outside of the ring. And then there's Prometheus, which is down here, which is orbiting on the inside of the F ring. So we have these two shepherd moons. Think about what a shepherd does, when they're, sort of guiding sheep through a pasture. They stay on the outsides and they make sure that they don't stray off the path. And so that's essentially what these moons act as, right? Little shepherds. So to summarize a little bit about Saturn's rings, right? They are made up of countless particles of ice, right? Individual ice particles. You can see the artist's rendition on the right over there. And they are extremely tiny, right? Which is why in this middle image, you can't really distinguish one clump of ice from another, right? They're very tiny and they're all very close together. And so it kind of just looks like a giant solid sheet of ice, a solid ring. And within that ring, within this giant looking ring here, there are these tiny gaps. And so the reality is it's a bunch of tiny rings that are sort of all concentric with each other, right? And so why is it that the Jovian planets have rings? Well, why don't we really see ring systems around the terrestrial planets? Well, it's probably debris, and there is far more material that got pushed that could rather condense in the outer solar system, right? You don't have ice orbiting in the inner solar system. It's just too hot. But in the outer solar system, where ice can condense, we see that there's a lot more material there to form these ring systems with. And they tend to be very faint and small. And that's why even though Jupiter and Uranus and Neptune all have rings themselves, we can't really see them with a naked eye. It takes a pretty high power telescope to be able to recognize the rings of those planets, because they are, they're small, they're dark, it's hard to see them, they don't reflect that much light, and there are far fewer particles than there are around Saturn. And this sort of wraps up what our conversation on planets from last week, where we were talking about moons, and just sort of how, picking up where we left off, we're saying not only are there all of these moons in the outer solar system, but some of them exist in pretty interesting places, like inside or around the ring system of Saturn. And that brings us to asteroids. And so asteroids tend to be pretty small by comparison to planets. The largest one is around 1,000 kilometers across. That is Ceres, all right, the largest object in the asteroid belt. And in the third bullet point, we have this number here that there are 150,000 asteroids listed in catalogs. And I'm sure that that number has updated, and there are many more than that now from the time that these slides were made. And if we start to think about, well, how small are we talking here with our asteroids? If we're looking in the range of 1 kilometer, there could be well over 1 million of them, right? Millions of asteroids, right? That are only 1 kilometer across by comparison to Ceres, which is, about almost a sixth of the diameter of the Earth. Excuse me, a 12th of the diameter of the Earth. And with that, it would make sense to say that there are more small asteroids than there are large asteroids, because as these asteroids move around in the asteroid belt and the inner solar system, they collide with each other, right? There are many asteroid collisions, and so it would make sense that there are more small asteroids than larger ones, because they keep breaking up. Every time one hits into another, it shatters and we get more pieces of asteroids. Now, that being said, if you took all of the asteroids in our solar system and you tried to somehow, or if you could accrete them into a single object, right, it would not have the mass of Mercury, right, the smallest of the terrestrial planets. Typically, when we look at asteroids, we're looking at asteroids that are that are not round, that are covered in craters, right? Remember that in order for something to become round, it has to have enough mass to pull itself into a round spherical shape. And in order for a celestial body to get rid of its craters, it needs to have some type of geologic activity, typically volcanism or tectonic plate movement. If there's an atmosphere, we can have weathering and erosion and deposition, which would smooth the surface out as time passes. But even so, even though all of the asteroids in the solar system wouldn't amount to a small planet, and even though they're very small, they're still interesting, right? We see asteroids that have their own moons. So here's Ida and Dactyl. Ida is the asteroid. Dactyl is the small moon on the right here. And you can get an idea of size. So Dactyl is, gosh, how big is Dactyl? Let's say it's maybe around 1 kilometer across, if I'm using the scale at the bottom correctly. Whereas Ida is somewhere around 45 to 50, probably closer to 45 kilometers across. But again, you can see it's, even at this size, it's not large enough to pull itself into a spherical shape. Right now, the largest of objects, like Ceres, or we mentioned Ceres is the largest asteroid, and also a dwarf planet. And Vesta, another example of an asteroid, are large enough that they are capable of pulling themselves into a spherical shape under their own gravitational pull. And so things that are large enough can make themselves spherical. Right? These are also very low resolution photos. And these were taken many years ago. And we discussed a little while back when we were looking at the different regions of our solar system. I don't remember which lecture it was in, but we talked about where we would find asteroids. And the majority of them would be found in the main asteroid belt, which exists between Mars and Jupiter. But there are other areas where there are asteroids, right? There are the near Earth asteroids, which are the ones that sort of fall within the orbit of Mars, right? So they don't orbit in the asteroid belt, they orbit in this region where Mars, Earth, Venus, and Mercury orbit. And so sometimes we concern ourselves with the asteroids that would cross Earth's trajectory, right, to cross its orbital path, right? Scientists are always on the lookout for whether or not the Earth might be hit by an asteroid. And then there are these Trojan asteroids, asteroids that orbit just ahead of Jupiter and just behind Jupiter, right? Equidistant from Jupiter in either direction. I'm going to draw that for you here. In either side, there's like this collection of asteroids in here. These are our Trojan asteroids, right? And so there are a bunch of asteroids. Oh, sorry about that. I meant to stop the drawing, not stop the slides. All right, here we go. Okay. So why do we think it is that there are so few asteroids beyond Jupiter's orbit? Again, most of the asteroids in our solar system are here in this main asteroid belt. Not really many beyond Jupiter's orbit, if any. So why do we think that could be? Here are a couple of options for you. Take a moment, type in the chat, say what you think. Okay, we've got a couple of A's, we've got a B. Well, the answer is not A, because, you know, as we indicated when we explored the interior of the Jovian planets, rocky material condensed everywhere, right? There was rocky material inside of Jupiter and Saturn, and Uranus and Neptune. So it's not that there wasn't rocky material beyond Jupiter's orbit. It's not that the heaviest rocks sank toward the center of the solar system. You know, this is not the same as like differentiation, which we touched on, which is when like the most dense material of a planet move towards the core and the least dense go to the surface. It's not quite like that. It's not that a passing star stripped those asteroids away, because it would have stripped away comets and planets too. The answer is C, right? It's the fact that ice is capable of forming in the outer solar system. And we'll come back to that. We're going to circle back to this in a second. So in the asteroid belt, you may be sitting there wondering, well, why isn't there a planet there? Why don't all of those, you know, those asteroids, excuse me, why don't all of those asteroids just accrete into a single object that orbits between Mars and Jupiter? And it has to do with something called orbital resonance. So, you know, Mars, you know, does laps around the sun every so often. Jupiter takes a little bit longer, right? So we could see here, Mars takes like just under 2 Earth years to complete an orbit around the sun. Jupiter takes just under 12 Earth years to orbit around the sun. And so there are times when Mars and Jupiter are either aligned on the same side of the sun, or are at opposition on opposite sides of the sun, or make a 90-degree angle between them and the sun. And we get this something called resonance, right? And resonance is basically, in this case, the combined gravity that just nudges on these asteroids and it breaks them up. And so we find that there are regions where there are lots of asteroids, right? And then there are gaps in the regions where there is orbital resonance with Mars and Jupiter. And it's this orbital resonance that prevents asteroids from accreting there, right? And so these particular regions correspond with orbital periods that are specific fractions or common fractions of Mars and Jupiter. And so it basically prevents everything from accreting into a single object. And so again, it's not that, you know, the reason that we have an asteroid belt here is not that there wasn't material for one. It's just that the resonance of Mars and Jupiter's orbits and their gravitational pulls on this matter prevented it from accumulating into something larger. Okay. So let's talk a little bit more about, well, let's actually move on to meteorites. So there's a little bit of terminology here that I'm going to share that's not on the next slide. Does anybody offhand know the difference between an asteroid and a meteoroid? If you can give a quick yes or no, so I know that you all have a pulse today. Okay. All right, that's fine, no problem. So a meteoroid is a piece of an asteroid or an asteroid that enters and approaches Earth's atmosphere. And then there are also meteors and meteorites. So let me differentiate now. So we have the asteroids, right? These big things that orbit around the sun. And then asteroids that enter Earth's atmosphere are our meteoroids, right? Small bits of broken off asteroid, right? Maybe there was a collision of asteroids that shattered and broke off into smaller pieces, and one of those pieces made its way towards Earth and enters Earth's atmosphere. It is now a meteoroid. A meteor is when that is the flash of light, it's the burning up of the meteoroid, right? So when the meteoroid enters Earth's atmosphere, it starts to brush or plow through all of these air molecules. And so there's a lot of friction. And it's that friction between the air and the meteoroid that causes the meteoroid to burn up. And we get this big, brilliant flash of light called a meteor. Now, there are always things falling into Earth's atmosphere from space, but many times they just burn up in the atmosphere, right? So like a meteoroid can enter the atmosphere, we'll see the meteor, and then before it ever reaches Earth's surface, it has already disintegrated because of all the heat. But if a meteoroid makes its way all the way to Earth's surface and there is something left over, whatever has made its way all the way down is called a meteorite. But the meteorite is the leftover. It's what we have, the relics that we have in our museums, the remnants of these meteoroids. And so there are two kinds of meteorites that we talk about. We have primitive meteorites, right? So, like you can see here, there are some simple rocks and metals. There's no real rhyme or reason to them in this stony one. In the carbon-rich one, it sort of looks like there are these little droplets of material, of like small things that maybe like hit the meteoroid when it was still accreting stuff. So as it's orbiting around the sun, and like really small droplets of things hit it and they like splatter out. That's what we're looking at here. Right, so we have these primitive meteorites, and then we have meteorites that are processed. Right, so there are some meteorites that come from meteoroids, that come from asteroids, that in the early part of the formation of the solar system, there are certain objects that got large enough or hot enough to differentiate themselves by density based on, so they differentiated based on material, which means there are some asteroids out there that have cores, right? Where others are just like random accumulation of stuff, like this rocky one with a little bit of metal flakes in it, or this darker rocky one with the small whitish compounds that hit against it. Right, these are our primitive meteorites, and these are our processed ones. And you can see, that they look much more homogeneous, right? They look to be like, this is metal through and through. This looks like something that like we almost like grew this metal. Like it doesn't look like there's any real rock in here. So this comes from the core of an asteroid. And then we have another processed meteorite, indicated at the bottom here that this resembles volcanic rock. So maybe, maybe this comes from a meteoroid where there was volcanic activity once, right? And that's why it's processed. It has a mixture of material in there. And so back in 2013 in Chelyabinsk, there was this huge meteor that made its way into the atmosphere, and everybody was able to see it. So I'm going to share that footage with you now. This is a compilation of people's footage, because apparently in Russia everybody's got a dashboard cam on their car. So let's take a look here and then we'll reconvene in a moment. Okay, we can pause there because it's a lot more of the same after that point. Let's get back to our slides. Okay. All right, are the slides still visible, everyone?
Do you know if any of those like meteors or like asteroids hit anybody?
No, they burned up in the atmosphere.
Oh, okay.
Yeah. But there are, I mean, let me pull up another video while we're still on the topic. There are other videos of meteors that have caused like window shatterings. Let me see if I can find a video here. Give me 1 second. Yeah, Chris, I mean, it's crazy how powerful these things are. Okay, so actually, you know what? Here's video footage from that same event. And you can sort of see here how like when there comes a point where like the largest flash happens right from the meteor, and it actually, when it explodes, it sends so much energy out that it sent this shockwave through that blew out like a ton of windows. Right, so while the meteor itself didn't hit anyone, it did cause a lot of damage.
It's like the pressure of it just like pushes.
Yeah, it's the explosion, right? Exactly. There's like this outward going pressure wave. It'll show more footage of things being blown up. And that's a lot of damage. Full-on buildings coming apart.
I thought it was like big craters.
Ни хрена дырочка. Ну козёла. Просто лакокраски.
Let me go back. I didn't realize we were so far into the video just now. Let's see if how this one goes. Look at that. Look at that trails. They're so close to it.
Ой. Охренеть. Где-то упал. Слышишь? Это знаешь, что было? Это он сверхзвуковой. Это, похоже, астероид. Это звуковая волна, астероид. Реально.
Сегодня какой-то
Куда-то уебал, слушай, он куда-то все-таки попал. Потому что только звук дошел, Коля. Куда прятаться? Это звук дошел. А, это звук дошел. Слышишь?
Что-то он упал куда-то, да? Ебать, а! Что это хуйня? Никит, что это такое? Бомбардировка, нахуй! Артподготовка, блядь! Да не сын, пока еще ничего нету. Артподготовка.
See how it took a second for that wave to finally catch up? It took a second for it to catch up to the after the what's it called? After the light passed by. My favorite part of all of that is how like there are so many people just on the road who don't skip a beat. Like they just keep driving. Right? Like nothing out of the ordinary, just your everyday meteor. All right, so let's take 2 slides to summarize some of the things that we just talked about. So asteroids are these rocky leftovers from the era of planet formation, right? Things that never quite accreted into anything larger. Why is there an asteroid belt? This is really, asking why is there an asteroid belt as opposed to some larger, accumulation of material that maybe makes another planet between Mars and Jupiter. And the reason is orbital resonance, right, from Mars and Jupiter that tugged on that material, preventing it from coming together. And how are meteorites related to asteroids? Well, most meteorites come from asteroids. Right? We have two different kinds of meteorites. We have the primitive ones, right, the things that are left over from the solar nebula. And then we have the processed ones, the ones that actually underwent some kind of differentiation where they sorted themselves out based on the density of their different materials. And some of them had cores, just like planets do. Right, now that brings us to comets. If you notice, when you look at a comet, if you ever look at a picture of a comet, comets have more than one tail. Comets have more than one tail, and the tail is actually not always behind the comet. If you're looking at this picture on the top right, or excuse me, on the top left here, we're looking at a comet that's coming in from the top left of this U-shaped orbit. Right, you can see the tail growing and growing in size, but the direction of the tail is always kind of like away from the sun, not trailing behind the comet itself. In fact, when the comet passes the sun, slingshots around it, the tail of the comet is actually in front of the sun. It's in front of the comet in its orbit. It's leading the comet. So tail can be a little bit misleading in that regard. Well, what exactly is a comet made of? And how will that help us understand why comets have tails where asteroids do not? Well, comets are basically these giant, like dirty snowballs, right? They're made up of dust, some metal, some rock, but a lot of ice, right? A lot of hydrogen compounds, right? So if you look in the list here, there's water, ammonia, so on and so forth. There are tons of hydrogen compounds and more. Right? There's carbon dioxide, there's carbon monoxide that make up this object. And inside of them, in addition to having this frozen gas, right, like this ice, there are different kinds of metals and rocks. So like titanium oxide, there are silicates, right? So we've got rocks in there. There's diamond, there could be graphite, so on and so forth. And these particles, right, these actual bits of dust are very small, right? Less than a micrometer across. And so we don't really have that many comets orbiting. I mean, comets do orbit within the frost line, but most of them orbit and are formed beyond the frost line, right? They are, as I've indicated here, the icy counterparts to asteroids, where asteroids are just these giant chunks of rock. Comets are tiny, tiny rock particles that almost act as the seeds for ice to condense around. And so comets are like these dirty snowballs, right? They're big balls of ice with little bits of solid rock and metal in them. Now, there are far more comets in the solar system than there are asteroids. And most of them don't have tails. A fact that usually surprises people when they hear that. Now, the reason that they don't have tails has to do with the temperature in the location where you'll find these comets. Right? The tail of a comet is the result of the ice, right, in the body of the comet evaporating. And basically, as the comet travels, it has gas that is being pushed off of it. by the solar wind and other ions. Right, so it's not until a comet actually orbits close to the sun, right, within the orbit of Jupiter, that it starts to grow a tail, right? Because beyond Jupiter, it's really not warm enough for these comets to start to evaporate. Right, and so what you can see here, there's like a zoomed in image of this comet. This is the larger image. This is actually a real image. This is not an artist's rendition of the Halley's Comet. And here you can see the nucleus of Halley's Comet. And you can see how the body of it has this like gaseous atmosphere, right? You can see the stuff evaporating off of it, right? This atmosphere around the body is called the coma, right? The coma of the comet. Right now, there are two tails, as I mentioned before. There's the dust tail and the plasma tail. The plasma tail is the result of the solar wind coming from the sun that is pushing that atmosphere in the coma directly away from the sun. So you notice how the plasma tail is directly opposite the direction of the sun. We could basically draw a line, a straight line through them. Now, the comet itself is moving down and to the right on our screen based on this pink arrow here. And the dust tail we can see is not, well, not quite directly opposite the sun. It is being pushed away from the sun, but it's also sort of lagging behind the comet a little bit. All right, and this dust tail is being pushed by photons. Remember, photons are particles of light. And these photons, are pushing on these bits of dust that are, larger in size and are a little bit harder to move. And so we get a little bit of curvature in our dust tail. So how does that tail grow? Well, let's take a look at the comet here shown on the top left. And so the nucleus warms and begins to vaporize into a gas. Okay, so we have this comet. It's going around clockwise in this elliptical orbit. And right around the time it reaches 5 astronomical units, or 5 Earth distances from the sun, that gas coma starts to warm up. And that gives us a nucleus around the sun. You can see, or sort of see here, it has like a little bit of a glow to it. That is the atmosphere of the comet. And it keeps moving in and getting hotter and hotter. And by the time it reaches right around Earth's orbit, it starts to form its tails. Right, so we have the plasma tail, which is being pushed away by the solar wind. Right, that's a stream of charged particles pushing on the comet's atmosphere. And then when it gets even closer, there's the dust tail, which is pushed by the light. And that would be the solar radiation in this diagram. The solar radiation doesn't have as much pushing power as the solar wind. And so we don't get as straight of a tail. It starts to lag behind based on the direction that the comet's moving. Right, so that's how you can sort of differentiate between the two. Right, and what we see here, right around this bottom part over here on the comet, close to the sun near the bottom there, that the plasma tail starts to almost get ahead of the comet. Right, and you can really see it here in this image, how the tail, right, the plasma tail is actually leading the comet around in its orbital path. And then it gets farther away, and the heating slows down, and the tails disappear, and then the coma disappears, it starts to refreeze, and then it just travels along as a little frozen ball in the outer solar system. And then it comes back and it does the whole process again. And we can actually predict when certain comets, like Halley's Comet, for example, will make their return near Earth. Now, when a comet passes by, and I'm going to toggle back and forth between this slide and the previous one, right? They have these small particles, right, that tend to follow the comet in its orbit. So like you can see here, larger particles are unaffected by sunlight or solar wind, and that's these larger particles that this dotted blue arrow is pointing towards. That, again, too big for the solar wind or solar radiation to push on them. And so Earth's orbit and the path of these larger particles intersect. And so these larger particles can enter Earth's atmosphere. And when they do, that is when we tend to have meteor showers, right? So meteor showers can be from comets as well. Right? It just, it's when we tend to have a lot of them happening at once. We call it a meteor shower. Meteor showers also tend to get their names from the constellation they appear to be coming from in the sky. Right? So like if you see here, this is the 2004 Geminid meteor shower, you would be looking towards the constellation of Gemini to be able to see those meteors. Okay. There's a lot going on in this image, and it's like pretty poor quality. So I apologize for that. But in our solar system, we discussed there are a couple of regions where we find asteroids and comets. Asteroids are found in the asteroid belt, and comets are found in something called the Kuiper belt. Right, this right here, Kuiper, K-U-I-P-E-R. The Kuiper belt is farther out. It's like outside where Neptune and Pluto's orbits are. Actually, kind of past Neptune, but really in the orbit of Pluto and around there. And it extends pretty far outward, right, to this much less dense region of the solar system. And even then, right, all these tiny little dots represent comets. And there are millions of them, millions and millions. But then there's something called the Oort cloud, which is about 50,000 astronomical units across and has billions of comets in this almost like a spherical shell around the solar system. And that's where most comets are. And so if you're wondering, well, why, we have these comets in a giant spherical shell around the solar system, how is it that we can see any stars beyond our solar system if we have all of these comets out there in a spherical shell? Well, one, the comets are very small. And they're very, very small. They're sort of orbiting randomly, but they're also so far away that you can't really see them. And they're very, very difficult to see. Right, so in the Kuiper belt, we have these comets with short periods, right? They take about 200 years to orbit the sun. That is considered short for something so far away. Their planes tend to be flat. Right, so they usually orbit around the sun in the same orbital plane as the other planets do. They orbit in the same direction as the planets. So if the planets orbit the sun counterclockwise from the North Pole down view, Kuiper belt objects orbit the same way. And then we have the Oort cloud. Right? And for comets to end up in the Oort cloud, typically what happens is there's some type of like gravitational slingshotting where a comet, maybe gets really close to a Jovian planet, these bodies with large gravitational pull, and it swings the comets around and out of their normal trajectory into the far, far outer solar system where the Oort cloud is. Oh. Now, that being said, of all of the objects, all of the comets in the Kuiper Belt, very, very few of them, or I should say a very small fraction of the total, actually make their way into the inner solar system, right? Most of them tend to stay pretty far out from the sun, especially if you're considering the Oort cloud, where we're talking about like 50,000 times Earth's orbital radius from the sun. Right? In the Kuiper Belt, we're more in the order of 30 to 100 AU, right? But even then, very, very few of the comets in the Kuiper Belt actually make their way to the inner solar system. All right, so I'm gonna take a moment to pause here and summarize. So how do comets get their tails? Well, they are essentially these giant chunks of ice that have formed around tiny microscopic particles of rock and metal, and they melt, right? They heat up and they evaporate. And when that happens, the sun's radiation and the solar wind push on that little coma, that atmosphere, and give comets their tails. Right? But again, most comets are very far from the sun, so they stay perpetually cold and do not have tails. Where do comets come from? There are two locations. There are the Kuiper Belt comets and the Oort cloud comets. Right? The ones in the Kuiper Belt orbit around the sun the same way that almost all objects in the solar system orbit. Right? And when I say in the solar system, I mean like the orbits of the 8 planets, right? So they all tend to orbit the sun in the same direction. They rotate the same way as each other, and they all orbit in a relatively similar plane. And then we have the Oort cloud, right? That's larger spherical distribution of comets that are so far out that we will never really have to worry about them coming towards the inner solar system. Okay, and with that, I'm actually going to end our slides here for now. And I'm ending the slides here, and I'll take any questions that anybody has. And then the rest of these slides, I will pick up with, oh, what just happened? There we go. The rest of these slides I'll pick up with in the evening section. So with that, you are free to go. You can head on out, people. If you have any questions, you can stick around. I'm going to stop the recording now, and I will see you all later.